All right, guys, these are two of my favorite tests. I love doing the ratio and root tests. So you can write these down. You have the rules for the test in your book. I'm just going to do examples of them because they are just super, super fun. So I'll let you go ahead and write down the rules for the test. There are theorems in your book, and let's get going. So example, and of course, blah, 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 determine if the following series converge or diverge, I think. Yeah, just converge or diverge. So let's do some of these. So what about something like s, k equals 0 to infinity of 2 to the k plus 5 all over 3 to the k. So when you're doing ratio and root tests, you got to kind of figure out which one you want to use. So in this case, because I have that plus 5 there, there are other ways we could do this one. We wouldn't have to use the ratio test on this. I actually could if I were to actually do this, I would break this up into two separate fractions. But just for fun, let's do the ratio test and see what happens. I don't want to really do the root test because if I took this, right, to the 1 to the kth power, guys, people, you cannot distribute that to each term. Don't do it. You may not do that, okay? We can't distribute exponents across addition and subtraction, so that doesn't really help me with the root test. So instead, let's do the ratio test. Ooh, I just love these. These are so much fun. Okay, so remember the ratio test, right? We want to take the limit, so we're going to get some number, we're going to call it r, and that r is going to be the limit as k approaches infinity. So basically we're taking the ratio of the different terms, and we're going to see what happens as we compare terms in the series as we get really further up. Are those terms getting really, really close together? Is one term getting really a lot bigger than the other? What is happening, right? So as I do this, let's take the limit then as k approaches infinity. Okay, so the kth plus 1 term, everywhere I see this guy, I'm going to put a k plus 1. K plus 1 plus 5 all over 3 to the k plus 1, right? And then I'm going to divide it by this kth term right here. But what happens when you divide by a fraction, right? Well, you just flip it good, and multiply. All right, and so let's see what's going to happen with this. This should be pretty interesting. So I'm going to simplify this a little bit, and the big trick when you're dealing with the ratio test, always when you're dealing with these, is to rewrite it by pulling off like this 2 to the k plus 1. This is 2 to the k times 2. Because what do you do with exponents when you multiply two like bases? You add them. So basically we're undoing that rule, right? So this is going to be 2 times 2 to the k plus 5. Okay, I need parentheses here, and then I have that 3 to the k on top. And then all down here, what do I have? I'm going to do the same thing with the 3. This will be 3 to the k times 3, all times 2 will to the k plus 5, right? And now this is where we can have some fun because my 3 to the k's cancel out. What else could I do here? I could pull that 3 out probably if I wanted to, but I'm not actually going to worry about that too much. But what are the heavy hitters here when I take the limits? These are the guys that are really driving what's happening, right? So what I'm going to do is I'm going to divide every single term by that 2 to the k because that's the biggest term in the denominator. So remember, when you divide, you don't distribute across multiplication, but you do distribute across addition. So if I divide this by 2 to the k, right, that just leaves me with a 2, and then I'm going to have plus 5 over 2 to the k. And then on the bottom, that 3 is just going to stay. This 2 to the k divided by 2 to the k is 1, and then I'm going to have plus 5 over 2 to the k. So see how that was a nice way to show us what is going to happen. So what's happening to this 5 over 2 to the k as k goes to infinity? Well, this guy's going to 0, right? The denominator is getting huge as the 5 is staying relatively small. This guy's going to 0 here. So what is the limit of this, of the ratio of these two terms? It looks to me like it's 2/3. Okay, so remember what the ratio test told us. If this number right here, r, that I found, if it is less than 1, then the series converges absolutely. So this guy is less than 1, so we have absolute convergence, which remember, absolute convergence is the same as saying it converges. So we're good to go. We're done. Converges. I love these tests. I think they're so much fun. Okay, I hope that makes sense. Let's do I want to do a couple more with the ratio. I want to do a couple with the root, and then we're going to call it good. I know it might be unusual because I might not go for like 30 minutes this time. Oh, let's get some factorials in here. I love working with factorials. I just think they're fun. This one's going to be a little bit nuts, but I'm excited to do this. This one, because it is going to get it a little bit nuts with the n+1s and the n's, I'm actually going to, I'm not going to worry right now about the limit yet. Okay, so let's just kind of consider, oh, I used n's again. People, I don't have anyone here telling me to pull myself together. Okay, that's what my son says. Okay. All right, so let's see what's going to happen as I take a sub k plus 1 divided by a sub k. All right, a sub k plus 1. Now, I'm going to go ahead and just get rid of all the absolute values. I know that k is positive. I know when I take the factorial, it's positive. So I'm just not even going to worry about the factorials, okay? So let's see what kind of happens here. So a sub k plus 1. So parentheses are important, people. Parentheses are important. That's all I'm going to say. That 2 is not just multiplying the k. The 2 is multiplying the k plus 1. Okay, so you must have it. Times, so that's my a sub k plus 1. Now I'm going to divide by the kth term, but when I divide by a fraction, it just means I flip and multiply, right? And so just kind of like we did with our, exponents above, how we kind of pulled one off, that's kind of the idea what I'm going to do here. We've worked with this before. I'm going to go ahead and simplify this guy a little bit. This is 2k plus 2, right? So let's simplify this a little bit. Notice I have a 2k factorial down here, and this is 2k plus 2 factorial. So I'm going to start pulling things off until I get what I want. So I'm going to take off one, I'm going to take off another one. If I took off another one, I'd be at 2k, and then the rest of it I'm just going to rewrite as 2k factorial. I still have the k factorial and the k factorial on the top. So you can see why I didn't bring the limit in quite yet. And then I'm going to do the same thing right here. I'm going to pull off a k plus 1, and that would leave me with the k factorial. That was for this k plus 1 right here. Then I'm going to do the same thing. I'm going to pull off a k plus 1. That'll leave me with a k factorial. That is for this one right here. And then what do I have left on the bottom? The 2k factorial. So I'm ready to start canceling. This is the fun part. So I can cancel the 2. Oh, wow. I could have just erased them, I suppose. I'm going to cancel the 2k factorials here. I have a k factorial here. And so what am I left with on top? I'm left with 2k plus 2 times 2k plus 1. So that's, FOIL that sucker out. We get 4k squared plus, what, 6k plus 2, I think, all over k squared plus 2k plus 1. And now I'm ready to take the limit. So I take it to the limit one more time. And what do we get here? It looks like we get, did I write this all out? We get 4, right? Because we have the same degree on top as we have on bottom. So we just take the ratio of their coefficients and go from there. And so 4 is greater than 1. And if that's greater than 1, what do we know about this series? It diverges. Okay, good. I don't know, that was pretty fun. Let's look at some of the root tests. So that's a ratio test, right? Let's look at a couple examples of the root test, and then we'll call this good. So the root test is going to be very useful anytime you have something that is like raised to the nth power. That's when it's pretty useful. So for example, let's say I have a series that looks like this, 1 to infinity of 4 to the n all over 3n to the n. So this one is just begging you to use the root test. Okay, I mean, if you think about what other tests we know, you could do the ratio test. A lot of times, the ratio test and root test kind of work together a lot. I'm going to tell you right now, usually the ratio test is a little bit easier. Like if you have factorials, it's going to be easier with the ratio test. Root test sometimes is easier if you have an n in the exponent, but not always, right? That first example, we had both, so we used the ratio test. But the root test says, if I take the limit of the square root, oh, I'm using n's again, people. The limit. Wait, please. man, as k goes to infinity of the nth, or nope, the kth root of that, the absolute value of the inside stuff. Now, I'm putting absolute value. I know that k is always positive, right? Because k is 1 to infinity. So I'm going to actually just drop these absolute values as we go. So now I'm going to take the limit as k approaches infinity. I'm going to take the kth root of each one of these, so that would just be 4, right? Those k's cancel out. And down here, that would just be 3k. What's happening as k goes to infinity? Well, the numerator's staying at 4, pretty small. Denominator's getting huge, so we are going to 0. And sure enough, 0 is, this is my r, right? Or no, in this case, they use rho. This is my rho. Is less than 1. So what do we know? It converges. It converges absolutely, which means it converges. Okay, pretty simple. I mean, I think I think it's kind of self-explanatory. It's a really short section. Let's just do one more example, and then we will we'll call this good. I'm trying to find one that might be, I don't know, a little bit more interesting, maybe. So let's look at this one. Now, this one, you know, I would argue that we could probably just do this one using the ratio test, and it might be a little bit easier. But I wanted to do this one because I want to show you one of the, oh my gosh, Sarah, you and your ends. I want to show you one of the, a limit that maybe you don't remember is true, and I want to prove this to you really quick so that you will remember it. Okay, all right. Great. I'm glad we had that talk. Good. So let's take, let's look at 2 to the k all over n cubed. So if I do the root test, right, and yeah, let's just do that. So I'm going to take the limit then as k approaches infinity of the kth root of this. If you don't want to do, you know, a lot of times I'll just take this to the 1 over k. Oh my goodness. I'm so sorry. Okay. It'll be fine. It's fine. 1 over k. So if we simplify this, remember when you raise an exponent to an exponent, you multiply them. So I'm going to take 1 over k times k. They'll just cancel, and I'll just get 2. And then here I get k to the 3 over k. So let's investigate this a little bit. And this guy right here, I could think of this as k to the 1 over k, all right, all cubed. And so let's investigate what's going to happen. I'm going to do a little bit of side work, or a little bit of underneath work right here. And I'm going to look at what happens to this guy right here. So this is actually an indeterminate form. This indeterminate form is infinity to the 0. And so if we're going to evaluate this, remember how we dealt with indeterminate forms like that. We let y equal what we're taking the limit of. Okay, I take the natural log of both sides. And so once we've established, the reason I'm doing this is because this one might come up. So this is one you probably want to remember. That once we figure out what the answer is, we kind of want to remember this one because it might come up when we're doing this root test. So again, natural log of y equals, now the reason we bring in the natural log is because we take that property of logarithms that tells us I can bring down that exponent, right? And sorry if you already know all this, but we're just going to go through it really quick. You can fast forward. Maybe you've already fast forward. So I'm going to take the limit of both sides, right, as k goes to infinity. Now what am I going to have here? That I have a natural log of k, and then on bottom I can just put that k. And the whole reason we do this is because now I have an indeterminate form, infinity over infinity. So I'm going to L'Hopital's it. So you tell me you're going to L'Hopital's by putting a little LH. You tell me the indeterminate form, that is infinity over infinity. So L'Hopital's tells me to take the derivative of the top, which is 1 over k, over the derivative of the bottom, but the derivative of the bottom is just 1. So this is 0. Now remember, that is the limit of the natural log of y. So what would the limit of actually y be? Well, to get rid of the natural log, right, we just e everything. So this would be e to the 0, which is 1. So all of this work right here to show that this guy right here and this guy right here, this guy is going to 1. Okay, so what is the top going to? It's going to 2. What is the bottom going to? It's going to 1 cubed, right? And so 2 divided by 1 cubed is 2. That guy is greater than 1. And so what do we know about this? A lot of work going on here. It diverges, okay, because it's greater than 1. So again, that's this guy right here is maybe one that you should kind of keep in the back of your mind, that the limit as k approaches infinity of k to the 1 over k is equal to 1. Hey guys, if you have any questions, let me know. Those are really fun. I love the ratio and root test. I think you're going to enjoy them as well. And yeah, have fun.